I don't want to be in English for 2 hours. Yeah. He gets an A for every hour. And I need a math or physics class.
I thought I had it. Was it up there and went away? Now it should go. There we go.
I almost forgot. So I was doing that.
What is that? What was that? All right, I just won't. Okay, let's get started. So for the written homework that was due today, let's do this one. I'll do it by hand without my... So you can, now that you've worked at them and thought about it, hopefully if I do one more example, this will really help. So we're going to look at how theta changes and how r changes with theta. Oh, first we got to write the function. So we do look at the max, the min, the midline. What's the max? The max is 5. The midline is min -1. So that means our vertical shift is +2. And our amplitude, or our distance up and down from the midline, is 3. And then, are we going to use a sine or a cosine or a negative sine or a negative cosine here? You're so smart. Sine, okay. And then the question is, now we have to look at, our period is not 2 pi. To get a full cycle of output values, we need 4 pi. So let's think about that. So what? So we need what's in parentheses to reach 2 pi when theta is what? So when theta reaches 4 pi, right? So when theta reaches 4 pi, we need the thing in parentheses for sine, what we're taking the sine of, to be 2 pi. That's the way you want to think about that. We need to get to 2 pi for sine, what we're putting into sine, but that has to correspond to when the theta value is 4 pi. So what do we need? What are we going to need here so that when I get to 4 pi, this thing in parentheses is 2 pi? 1/2, right? Does that make sense? So that's going to get me what? In the parentheses, it'll get me to 2 pi when theta reaches 4 pi. Okay, so that's the equation of the graph. You could also write it as a cosine with a shift. There's many ways to write the same sine or cosine curve. And so here we go. Let's do blue or something. So, and we're going to go as we go from 0 to pi over 2. R goes from? So this graph tells us that as we go from 0 to pi over 2, R goes from 2 to 0. All right, 2 to 0. So that means we're going to start here at 2. And then it's going to head down. What does head down mean? It means that as we turn this angle, we get closer and closer to the pole. And then when we get to pi over 2, we're at the pole. So getting closer. So this is, do you see that? That's decreasing R there. Right? So each angle has an R value closer to 0 than the one before. That's decreasing R. Is that a question?
From 0 to pi halves, isn't it a little bit less than, or you get a little bit less than 0 because the sine of 1/2 times pi halves would be pi 4, so that's right 2 over 2 times -3 plus 2 would be a little bit less.
Yeah, you're right. It doesn't go through exactly through 0 there. But it's so close that for graphing, sketching purposes, it's close enough. But yes, you're right. Okay, so then from about pi over 2 to pi, what is our, now we're in negative territory here, right? So negative what to what? Or 0 to what? 0 to -1. And so that's in this quadrant, right? So quadrant 2, sweeping from pi over 2 to pi. But our R values are going to go from 0 to -1. So where will the graph appear? Which quadrant? Fourth quadrant, right? Okay, so then they're going to go from 0 to, by the time we get to pi, we're at -1. So our R values are going to get more and more negative until we reach -1. So now we're at angle pi, but we're at R equals -1. And then we go from -1 to 0. I'm not wasting your time. Some people are not paying attention. I'm not wasting your time. -1 to 0. And as we go from -1 to, as we go from pi, so we're in the third quadrant here, right? Third quadrant, pi to 3 pi over 2. Pi to 3 pi over 2. Our R goes from -1 to 0. So what would that look like? What quadrant will that graph in? The first quadrant. So the first quadrant, here's -1, and then by the time I get to 3 pi over 2, I'll be at 0. So here's those R values getting less negative from -1. One more try. I don't know why my hand just goes left. Okay, got it. So that's those R values. We're sweeping in this quadrant for positive R. So -1 and then getting closer to 0. And then we're going to go from what? 0 to 2? In the fourth quadrant. So starting at 0, and then we're going to end up at 2. So R is getting greater and greater and greater and greater. So do you see how for increasing angle, at each angle that I increase, my R is getting greater and greater and greater there? Do you see that? So our minds are thinking X and Y, right? We think down and then up. But no, you got to see that this is continually increasing R. That's what continually increasing R looks like. Closest to the pole for these angles, then further and further and further and further from the pole. Okay, but we're not done, right? So we've got this whole different part of the graph, and we're all in positive territory now, so that's nice. We start at 2, or 2 pi is it 2? Yeah. And we're going to go from 2 to what? So from 2 pi to 5 pi over 2. We go from 2 to 4. Is that right? So starting at 2. So R, do you see R is increasing, 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 increasing. Those all, as you sweep through the quadrant, those are all, those points are a greater R value than the one before. And then from 5 pi over 2 to 3 pi, which will be back to pointing left, R goes from 4 to 5. So from 4 to 5 as I go through this quadrant. Something like that. And then back from 5 to 4 in the third quadrant. Let's try it again. There we go. Back to 4. And then from 4 to 2. 4 to 2. Not too much of a, try it again so we come in at the same angle we left at. There we go. Questions? Could you do it, right? So this is on the final. No calculator, just the way I just did it right here without any technology. Besides the projection and my, no technology that helps to sketch it. Chance for questions. Okay, so let's keep going here. Got one more. So the last today's topic is on like the calculus of polar functions. So we We're just now spent some time like learning our way around the plane, plotting points, how negative r's work, sketching graphs. So now we got to do a little calculus. So first thing I want to say is, let's talk about, we know r is a function of theta as our main functions here. So what would it mean? Derivatives of these functions would be of the form dr d theta. What would it mean if dr d theta was 2.5? Here's our one and last chance to prove we got it. Everyone's talking to somebody. Tell the person next to you. What does it mean that dr d theta would be 2.5? Okay, so volunteer. dr d theta is 2.5. What does that number 2.5 mean? Dylan.
As theta increases, the radius increases at a rate of 2.5.
And what does that mean? The radius increases at a rate of 2.5. That's the rate of change of radius with respect to theta. And what does that mean? If it's the rate of change of r with respect to theta. What does that number 2.5 mean? Right behind him.
I think for any change in theta,
Okay.
your change in radius would be your change in theta times 2.5.
Given any change in theta, to get the corresponding change in radius, you'd multiply by 2.5. Okay. 99 out of 100. A plus. But we got one little thing we got to add. What's one? Yeah. Okay, so and is it a constant rate of change? So like if I have any r as a function of theta, do I have constant rate of change for all theta? Yeah. Yeah, so since like the rate could be changing, we'd have to say that theta is a small change, right? So if you have a changing r for theta, then or like all these graphs we've been doing. For instance, 2 cosine theta plus 2 has a changing rate of change. So we would say for a small change, right? For any small change in theta, the corresponding change in r would be 2.5 times that change in theta. Okay, so I've drawn little parts of, say, 6 functions here. Okay? So I want you to analyze dr d theta. Dr d theta. Is it a big or small, positive or negative value, or maybe close to 0? So big, that means a big positive. That means just positive equal to 0, negative, or a big negative. So big or small, positive or negative, or 0 at each of these points. And so we're going to look at how does theta change? How does theta change? For increasing theta means what? Counterclockwise. So you have to be tracing, in your mind, you have to trace over this curve in a counterclockwise manner, and then you're analyzing what r does to determine if dr d theta would be big or small, positive or negative, or maybe close to 0. So now notice, what have I drawn all the same about them? What quantity is really the same about all these? Yeah, which would be what? Slope would be. But this is rate of change, right? What rate of change? dy dx, right? So for all of these, dy dx is big or small, positive or negative? Big positive, right? For a small change in x, you get your y shoots up, right? For a small change in x, you get a large change in y. And it's the same for all of them, right? It's the same for all of them. But you're going to find that dr d theta varies greatly for all these, okay? Dr d theta is you're going to be choosing from all these in different examples. So take a couple minutes. You're thinking if this curve was traced counterclockwise. These are all just little bits of these curves. And you got to imagine tracing counterclockwise and then asking what r does to determine what dr d theta would be. All right, everyone's talking to somebody. Go. Here's constant r. That's constant r, right? Do you see that that's constant r?
Yeah.
So is r increasing a lot or a little?
So
I think a lot
always
of
positive
because if you're going like that way, then it looks like a lot.
See, this is constant values of r, right?
But
So
if you're going
I'm so glad you're having fun, though.
I don't know. I don't get that.
So you think of values of r like this.
Oh, so it's
Yeah, to see that it's increasing a little bit. What would it look like if it was increasing a lot?
would that be 3?
That would be r increasing a lot, right? Because as you turn this way in theta, your r's increase greatly. Is it better? So this is just increasing a little bit. So it would just be,
Do you want us to determine like how much it's increasing at each point?
no, just these are your 5 choices. Just make these 5 choices. So this one, no. A little bit, sorry, I wrote it wrong.
Like you're looking at your where does the radius change?
Okay, so you might have overheard our conversation about F1. That's positive and not super huge positive. Do you see that? That R values are just increasing kind of gradually here. Compared to, I've drawn a constant R value in red. So for F1, I would say it's like just a moderate increase in R. So it's a positive, but not a super huge positive dr d theta. Does it make sense? Okay, so what about the next one? So negative, and is it significantly negative or just a little negative? Somewhere in between. You know, it's like, you know, yeah. So if you chose either one, just as long as you got this one as negative, you could make an argument this is decreasing greatly, or not so great. You know, so maybe somewhere in between. But negative is the key there. That as you go clockwise, values of R are decreasing. Yeah.
I'm a little confused where the red lines are coming from.
Constant R.
So that's what, like the R.
Constant R would be parallel to these circles, would be keeping R constant. So it helps you to see that this is a greater R here then this is here. Or R is decreasing as we're going counterclockwise.
Oh, that makes sense.
Great. Yeah, so the red, I'm drawing the red one to show constant value of R. All right, how about F3? What function 3? Pretty close to 0. It's like keeping a constant R as you turn counterclockwise along this graph. So about 0, the rate of change. Okay, what before? Where's my pen? Increasing, decreasing. Yep, it's increasing, right? As you go counterclockwise, R values are you're further from the pole. So again, constant R would be around on that. That's like constant R, and so as you go counterclockwise, your R's are increasing, so your dr d theta is positive. All right, F5. Decrease or increase? So we're going this way. Here's constant R. Something like that is constant R. So R values are decreasing kind of rapidly there. And finally, F6. About 0. Right? R is like staying constant as we go counterclockwise. Does it make sense? So again, the point that I drew them all with the same slope, xy slope, so they all have a big, slope, y with a function of x, but totally, they're in the polar plane, it's totally different, right? They have all different rates of change based on whether we're getting closer to or farther away from the pole as you go around counterclockwise. Okay, so let's work on this one here. How about R equals 2 cosine theta plus 2? So can we sketch that in rectangular coordinates and polar coordinates? What's the period? 2 pi. Right, we just have theta, so its period's 2 pi. What's our midline? Midline is 2, max at 4 minutes 0. I'm going fast here, but you've done lots of practice of this recently. Where does it start? Min, midline, or max? Cosine starts at the max. So we'll break up our midline into 4 equal quarters. And then cosine goes something like that. And then we'll sketch this. I'll make it pretty on the computer here. So as we go from 0 to pi over 2, our values go from what to what? 4 to 2. And so and they go from 4 to 2. Starting with a high rate change of R or a lower rate of change of R? Yeah, it looks like it's going to like hover close to 4, and then as we keep increasing angle, then it's going to shoot towards 2 faster. Do you see that? So this is like a low negative rate and then a higher negative rate. So what will that look like? It hovers closer to 4 at the beginning, and then it shoots down to 2 as we get close to pi over 2. You definitely don't want to draw a straight line here. Straight line from the 4 to the 2. If you do that, then look at what happens. If you draw a straight line from 4 to 2, what's happening to R right here in my straight line? R is increasing, right? So this is like wrong. So not only it's a bad sketch, but it's wrong because R would be increasing here when R decreases the whole way. Do you see that? So again, we want we want R to hover close to 4, lower rate of change, then decrease rapidly to 2 at the end. Oh no. That's not what I want. I want to be in this. There we go. Okay, so let's watch it. Here it goes. Staying close to 4 at first, and then decreasing rapidly. And then in the second quadrant, back to 0. So R is decreasing as we sweep, and then ending up at 0 when we get to pi. So that's 4 to 2, and then 2 to 0. But then, third quadrant, back out to 2, and the fourth quadrant, 2 to 4. So this is called a cardioid, right? It kind of looks like a heart a little bit. It's called a cardioid. And I'm interested in, I want to figure out what this point is closest to the top of the screen. So there's a point here that's closest to the top of the screen. So is that a matter of R? What are R values doing all through here? They're decreasing the whole way. So there's nothing special about R there, but there's something special about what coordinate there if I want it closest to the top of the screen. He wants Y. Yeah, so this is a matter of the Y coordinate. But we're dealing with an independent variable of theta, right? So now we're like truly meshing together the polar coordinates and Cartesian coordinates, because that highest point, wherever that highest point is there, between here and here somewhere, would be a matter of looking at dy d theta, right? For a change in theta, we want dy d theta to be no change in y, right? So the very highest point, we'd see no change in y for a change in theta. Okay, well, in order to do that, we need to know what y is. What is y as a function of theta? What is y as a function of theta? How do we get y from r and theta? Remember what it was? R sine theta, right? But what's our r's? Our r's are according to this curve. We want to stay on this curve. And what is true about r on this curve? R equals what? 2 cosine theta plus 2 is what r is on that curve. So that's, for this curve, y values, here's the y as a function of theta. It's the r value, just the function r's, times sine theta. So when I do dy d theta, how do I find dy d theta from this equation right here? I'm going to set it equal to 0, but I gotta get dy d theta first. What's it going to take to get dy d theta? Derivative, which means doing product rule, right? So this is one thing times another, so we get product rule. So it's going to be derivative, and I'm going to use C and S for cosine and sine. It saves a lot of writing and space. So it works good as long as you know what you're doing. So do negative 2 sine theta, it's the derivative of the first, times the second, plus the first, times the derivative of the second. So that's product rule. Product rule on our y as a function of theta. And what do I need? I want that to be equal to, I want to set that equal to 0. Okay, multiplying it out, it is negative 2 sine squared theta plus 2 cosine squared theta plus 2 cosine theta So now I've got sines and cosines. It'd be nice to have just one of those, not both. I've already got two terms that involve cosine, so can we switch sine squared into cosine? What would it be?
1
I can use the Pythagorean identity, do 1 minus cosine squared. And if I do I distribute and combine terms, I'll get positive 4 cosine squared plus 2 cosine minus 2. Make sure you agree with my math. Because it's equal to 0, we can factor out a 2 and divide by 2 because it's equal to 0. So we're going to divide by 2 and get cosine squared plus, 2 cosine squared plus cosine minus 1 . So that's a quadratic. So it's similar to like 2x squared plus x minus 1. It's just instead of x's, we have cosines. So does it factor? We've got a quadratic. Does it factor? So I got to multiply to negative 1 and add to positive 1. Can I do it? I think if I make the positive with the 2 and the negative with the 1, then I add the positive 1. Does it work? Yep. So there's two ways I can get this to be 0. What is this? Again, what is it? dy d theta. We're saying we want, for changes in theta, we want to be at a constant y value, non-changing y value. One of those points is at the very top there somewhere. So this one here gives us that cosine theta is a half. And this one is cosine theta negative 1. As long as one of those two things happen, then my equation equals 0, right? So for what values of cosine theta, or what values of theta do I get cosine as a half? Do you remember? And cosine is the x-coordinate, so we're talking about either the first or fourth quadrant. Remember? Nick remembers? Yeah.
pi thirds.
Pi over 3. And then there's also in the fourth quadrant where cosine is positive. 5 pi over 3. So that's along this, that's one of our lines here. It's actually this line here. So does it look like along that line, that gives us the highest point. And then 5 pi over 3 is this one here. Does that look like also dy d theta is 0? Yep. So right, for a change in theta, dy is not changing, right? So we're not going up or down for a change in theta. And then where else? Cosine theta is negative 1. That's that. Pi, does it agree? So what are we saying? As we come in here, what must happen? As we come into at pi, it must flatten out. Right as it gets to pi in the pole, it must like flatten out. You can zoom in a little bit. See that? So you see how as you get close to the pole there, that is right when you get there to pi, it's gonna flatten out and there's gonna be no change in y when you get to pi, coming from both directions. So then how would we get, I want the polar coordinates of our highest point and the Cartesian coordinates. So what do we know? Of those, what do we know now? We have theta, right? We have theta is, that's our pi over 3. How would we get r? Yeah, the function tells us, right? The function tells us r values for every theta. So we're going to plug it into 2 cosine theta plus 2. So this r comes from right there. And then how do we get x and y given r and theta? 2. Yep. X is always r cosine theta, y is r sine theta. So then we can get both the x, y coordinates and r theta coordinates. Doesn't make sense. Okay, find dx d theta. Go, find dx d theta. What would that be? For this function, for 2 cosine theta plus 2, how would you find dx d theta? I got -4 cosine theta sine theta minus 2 sine theta. Does somebody else get that? I got 1, got 2. Okay, so we got lots of confirmation on that. So if I were to set that equal to 0 and solve it, what would I be finding? In terms of the graph, what would I be finding in terms of the graph if I set that one equal to 0? You know, CJ? So set that equal to 0, the dx d theta. You sure? Okay. What would we be finding? Yeah, Freddie?
Is it the leftmost point?
Okay, and also? Yep, so it's wherever x does not change for theta changing, which would be your like vertical tangents. So that's going to give you the leftmost and the rightmost points. We won't do that for time's sake, but if you set that equal to 0, that's what you'd be finding. You'd be finding like the left point here, the left point there, and then it should give you the rightmost point here. What I do want to start talking about is I want to find the equation of that orange tangent line. So that's at pi over 2. And when we write the equation of that line, is it going to be most convenient to write it in x and y or r and theta? Certainly x and y, right? So polar coordinates is not nice and neat and compatible for oblique lines through the polar plane, as we saw in the previous, I think last time. So we want to write that in terms of x and y. So what things do we need to write that line in terms of x and y? What do we need? Yeah, all of you are saying it, slope and a point, right? So, and the slope would be, we want dy dx. But we're not going to get that from y as a function of x, right? That would be, trying to change this cardioid curve into y as a function of x would be awful, if not impossible, right? So this, we don't, cardioids and xy coordinates don't mix, right? This is a polar, suited to polar, nice easy polar function, but not y and x. So as we do dy dx, we want to do it in terms of theta. We don't want to try to change everything in terms of x. So what will dy dx be in terms of theta? So we saw this before with parametric functions. How will we find that? How will we find dy dx? What will we do? I think lots of you are thinking that. Right, so we're going to do dy d theta, which we have. And you guys just found dx d theta. So it's going to be, we could use any one of these here before we divide it by 2, right? So any one of these would be our dy d theta. So let's just go with this one here. So 4 cosine squared minus 2 cosine minus 2 was our simplified dy d theta. And then we just came up with minus 4 cosine sine theta, or cosine theta sine theta. Minus 2 sine theta, made it. So what is this? This is, for any point on the curve as a function of theta, it will give you the slope dy dx. Okay, so for given any theta, so what will we plug in to get our slope? This point right here is theta equals pi over 2. So I'm going to plug pi over 2 into that. We won't do it, but pi over 2 to get slope, m, right? That'll be my m for this line, and then I'll need the coordinates of this point, x and y. How will I get that? Well, we know the x-coordinate. What's the x-coordinate at pi over 2? 0 already, so we just need the y-coordinate, and we can just do r sine theta. Y is going to be r sine theta. Again, r is that. Sine theta just be 1. Right? It's going to be the value of r at pi over 2. So it'll be 2, right? So the point will be 0, 2. X is 0. Y is 2. And the slope we'll get from this putting pi over 2 in there. And what would you just predict the slope to be, looking at that? Close to what? Looks pretty close to 1, right? The slope for a change in x, we got about the same change in y, right? Pretty close to 1. But you have to make sure, verify that. Okay, so you can finish that. Slope, point, equation of the tangent line. Okay, any questions? So that's our polar, that's kind of doing some calculus and polar coordinates. Okay, Canvas quiz, but then I want to talk business after that. Do not leave after the quiz. Any questions before I erase?
Is an integral of a four function similar to parametric, or basically just like sine area?
Yeah, we can do a sign. That was the next topic. We just ran out of time. I'll post the video. You can watch the video. It's actually really cool. It's a cool demonstration using GC. So, but no time.